Taphonomy is the study of what happens to an organism after death, and it can give us really interesting insight into the lives and death of our ancient ancestors. By examining the processes that affect remains, we can learn not only about their lives and deaths, but also things like information about the climate. And for hominins, we can even use taphonomy to start to begin to piece together their beliefs. One fascinating application of taphonomy is in the study of early hominin burials. Taphonomy helps us differentiate between natural and human-made burials. For example, deliberate burials often involve the body placed in a specific position, either lying on the back with the arms crossed over the chest or in a flexed position facing a particular direction. To determine if the positioning of a body is intentional, taphonomists look for evidence of scavenger activity, such as carnivore or rodent bite marks. If the remains have been untouched, it's way more likely that they were buried quickly and deliberately, protecting them from exposure to scavengers. Taphonomy can also reveal how our ancestors died. Some Australopithecine fossils, for instance, show clear evidence of carnivore tooth marks, sometimes even punctures from saber-toothed cats. This tells us that, at one point in our evolution, humans weren't exactly at the top of the food chain. One striking example comes from the Bodo cranium, a Homo erectus fossil from Ethiopia. Cut marks on the skull suggest defleshing activity, an early form of human tool use and possibly a ritualistic practice. Taphonomy has even helped us understand the scavenging behavior of ancient predators. In Zhoukoudian, China, researchers found that remains of over 50 Homo erectus individuals were scavenged by cave hyenas during the Pleistocene era. Their bones showed bite marks and breakages consistent with hyena feeding patterns. Taphonomy doesn't just apply to human remains. Fossilization, the process by which organisms are preserved as fossils, tells us a lot about the environmental conditions of the past. But it's rare for an organism to become a fossil. After death, most creatures are broken down by bacteria, insects, and scavengers. For fossilization to occur, several factors must align. First, the organism needs to be protected from scavengers and weather. Rapid burial, especially in stable environments like wetlands, plays a crucial role for this. Wetlands can slow down decay because they create anaerobic conditions, meaning there's little to no oxygen for bacteria to thrive. After burial, sediment accumulation begins. Sediments cover the remains and eventually mineralize the bones, turning them into fossils. This process, known as lithification, squeezes out excess fluids and replaces organic material with minerals from the surrounding soil. The result? A mineralized copy of the original organism, which can last millions of years. Did you know that the most common fossils we find are actually plants? Even ancient forests have left us clues in the form of petrified wood, where trees have turned to stone over time, preserving every detail of the original trunk's composition. These fossils provide a snapshot of ancient ecosystems, showing us what the climate and environment were like millions of years ago. Human fossils, or human ancestor fossils, however, are much rarer and are usually incomplete. Lucy, the 3.2 million year old Australopithecus afarensis, is one of the most famous fossil finds. Discovered in Ethiopia in 1974, her remains are only 40% intact. Even older fossils, like Sahelanthropus tagentis from around 7 million years ago, offer crucial clues about the evolution of early hominins and our lineage's divergence from other primates. We also find fossils like coprolites, which are fossilized poop, and bezoars, the stone-like remains found inside the intestines of fossilized creatures. We can use both coprolites and bezoars to learn about the diets of these organisms, their health, and even their surrounding environment. Some fossil sites are really unique. Take the La Brea tar pits in Los Angeles, where animals like mastodons and saber-toothed cats were trapped in asphalt, a form of crude oil, during the Pleistocene. Their remains, perfectly preserved in the sticky substance, offer a glimpse of what the area looked like over 10,000 years ago. Things like footprints can even become fossilized. Trace fossils are geological records of activities and behaviors of past life, like fossilized nests, burrows, or footprints. But you don't preserve the organism itself. They're formed when the organism interacts with a soft sediment, like walking over mudflats, and they form into fossils when these traces are covered over with new sediment before they can be washed away. Whether it's ancient human ancestors, dinosaurs, or even fossilized poop, each fossil tells a story about life on Earth millions of years ago. Taphonomy helps us piece together that story, revealing how organisms lived, died, and were preserved.